All right, everyone's favorite part of any lesson is the applications. We're going to be doing problem solving here now. Last part of the functions unit for trigonometry. Let's get started by looking at this one. When the last person gets on a Ferris wheel, it begins to rotate. So make sure you know what a Ferris wheel looks like. It's a big circle. It's being held up off the ground. And you've got little things that you sit in. So we're talking about this last one as the last person gets in. And then the Ferris wheel goes up and around back. So that's what's happening. We're talking about the height above the ground. So we start here at some height above the ground when you get in. They go higher, 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 and then you get to a maximum height, and then they start coming back down. Same thing's happening here on this graph. We get in on to the Ferris wheel, it goes up, we get to a maximum, and then we come back down to the minimum, around and around. And it's periodic because it's going the same speed all the way around. So then let's read this graph. Where do we get onto the Ferris wheel? Well, that's at its minimum point, the lowest point on the graph. We know that it better be above the ground, above the zero. So we look at it and say, oh, that is 5 feet. What's the radius of the Ferris wheel now? Well, I want to know, how far is that distance? Well, that radius is half of the diameter. And if we look at it, the diameter is going to be the distance from the maximum to the minimum. Maximum to the minimum diameter. Halfway in between is our radius. So let's find that radius value, which is at 45. So we know that that whole diameter there is 40. So then the radius is half of that, 20 feet. If the radius is 20 feet, think about what part of the graph, of the equation, is the radius actually talking about? Oh, that's the amplitude. And then we can say, what is the time for one revolution of the wheel? Well, we start at the beginning. When will we get back to that same spot? Right here. And it'll be at 2 minutes. The thing that I want you to notice right now is every time that we have graphed up to this point, the x-axis has always been in radians or degrees, usually in radians. But now we're going to be putting it into an application where the x-axis is going to be actually talking about usually time or something that is not an angle of the graph. We're going to have to adjust for that in the equation. And the same process, it's identical process, it's just going to look a touch different when we write the equation down. And this is what I was talking about, right here. When we have our equation, usually up to this point, inside our phase shift was talking about angles. It was pi over 2 to the right, something like that. But now we're going to be having a number. Our b value was usually just a number, but now it's going to be having pi attached to it. Applications are naturally occurring things, so therefore we must always do applications in radians. All right, applications always in radians. All right, let's sketch this graph now. Okay. Let's start by identifying all of our parameters here. Our A is 3, so that gives us our amplitude. You know what amplitude is? 3. Our B value is pi, so that's going to give us our period. Our period it allows us to find our period. B and period are not the same thing. The period is 2 pi over the b, or 2 pi over pi. Our period is 2 units of whatever the units are. C value is 1, so that means it's 1 unit, the phase shift is 1 unit right. And then our D value is equal to 2, so that means our vertical displacement is 2 units up. C and D have positive or negative sign attached to them. The phase shift and the displacement are talking about direction, up, down, right, left, that kind of thing. When you're graphing something like this, I suggest you start with the first 2 stretches, your A and your B, just to get a visual of what that looks like. And then from there, do the translation of that up, down, right, and left. Okay, so I put my axes on there. And I'm going to go up by a scale of 1 on the y-axis. So 1, 2, 3, 4. 1, -2, 3, -4. And then on our x value, we're told that we want to go between 0 and 4. I've got a bit of space here. I'm going to go by, I only need 4, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8 tick marks. So I'm going to put 4 there, 3, 2, and 1. So I'll go by 0.5 on each scale there. Start by graphing the A and B part. So I'm going to graph in, let's make it in blue, y equals 3 sine of pi x. Leaving off my C and D, just so I can get a visual of what's going on. No translations, so the sine would go through 0 and 0, just like regular sine. Amplitude of 3. That means it's going to go up to a maximum of 3, but I have to figure out where that's going to occur. Well, my period is 2, so I'm going to be starting back at the 2, and then I'll be back at the 4, going upwards in the same direction. A sine graph is always broken into 4 parts. Same with a cosine. There's 1 period of sine. So in 1 cycle, we can break it into 4 parts. Okay, so from the midline to the midline, and midline to midline. There's 2 parts, but each of those 2 parts is broken into another quarter. Midline to maximum, maximum to midline, midline to minimum, minimum to midline. 4 parts. Color coordinate them there. Part 1, part 2, part 3. Put the blue back in there. And part 4, pink. So those 4 sections are evenly distributed always. They're always 1/4 of a cycle. Because I haven't done any translations up, down, right, left, no phase shifts, and no displacements, I know that within 1 of those cycles, talking about from here to there, from 1 to 2 there, halfway in between, it's going to be back at the midline. This spot right here. Halfway in between there, I'll be at my maximum. Okay. And the maximum was 3. Halfway in between these 2 midline, don't think of it as the intercepts, as the midline spots. Halfway in between there, I'm going to be at my minimum, which will be -3. Let's connect our dots. And do it again. Halfway in between the next cycle, we'll be at the midline again. Halfway in between a max, halfway in between a min. Connect them up. There's your 2 cycles of y equals 3 sine of pi x. Now we're going to do our translations. Take all those points, 1 right and 2 up. I'll do it in green. So 2 up, 1, 2, and 1 to the right. 2 up, 1, 2, and 1 to the right. 2 up and 1 to the right. 2 up, 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 1 to the right. 2 and 1. 2 and 1. Let's connect those dots there. But we're asked to do between 0 and 4. I haven't started at 0 with this so far, and I'm going past 4. I can only go here. So I need to take my graph. I'll do it in a darker color so you can see it. Make sure you hit it. And I need to lop off one part of it, which is this part over here. I don't need that part, but I do need to put the other part onto the left side from 0 to 1, or 0 to 0.5. Okay, I'll take and do this one in green now. So we're going to take every point. We're going to move it 2 up. So 1, 2 up, and 1 to the right. But be careful with your scale. Our scale is 1 for every 2. It's 0.5. So I got to go 1 to the right over to here. So 2 up, 1 to the right. That point's going to go there. 2 up, 1, 2, and 1 to the right. 2 up, 1, 2, and 1 to the right. Careful with your scale always. 2 up, 1 to the right. Oops, looks like I messed something up here somewhere. Oh no, just forgot one point here. 1, 2 up, and 1 to the right. There, I forgot that point. There's our first cycle. Remember that we can only go from 0 to 4. So then I'm going to take my next points and keep moving them. 1, 2 up, and 1 right. 2 up, 1, 2, 1 right. I can stop there. I've hit my end, which was at 4. So I can stop at that point. Now I have to work on the left side with a part of the graph that I didn't have before. Continuing our pattern, it would be 1 there and to there. There we go. That last point doesn't go to there. That last point goes to the midline. There we go. That's better. Careful with that last point where I put it. A little bit of brain fart there. Okay, so that in green, we now have y equals 3 sine pi x minus 1 plus 2. And as I just talked to you, we've always had on sinusoidal graphs, the x value, their horizontal axis was in terms of pi. We're not going to be using that for anything that's an application, such as oscillation of a spring up and down, rotating of the Ferris wheel, tides going in and out, the daylight during a year goes up and down, up and down. And these things go up and down just like a jump rope, just like life. All right, just like life, the trig might get hard here too, but you keep on going. Looking at this first example, I'm going to let the lady explain their example before I get into ours, just so you can see the process to go through.
The Singapore Flyer is the world's tallest Ferris wheel. People ride the wheel in capsules. The wheel has a diameter of 150 meters and completes one revolution in approximately 32 minutes. A capsule reaches a height of 165 meters. Part A. Determine a function that models the height, h meters, of a capsule at any time, t minutes, after the wheel begins to rotate. First, I'm going to sketch a diagram. The wheel has a diameter of 150 meters. A capsule reaches a height of 165 meters. So, the minimum height must be 165 meters minus 150 meters, or 15 meters. I can use a sinusoidal function to model the motion of a capsule because it travels along a circle at a constant speed. I'll sketch a graph of the function. The capsule starts at the base of the wheel, so when time is 0, the height is 15 meters. I'll plot a point at 0, 15. Since 15 meters is the minimum height of the capsule, this is a minimum point on the graph. The capsule will reach the maximum height of 165 meters when it's made half a revolution. It takes 32 minutes for the capsule to go all the way around the wheel, so it'll take 16 minutes to go halfway. So, when time is 16 minutes, the height is 165 meters. I'll plot a point at 16, 165. This is a maximum point on the graph. The capsule will be back at the minimum height when it's made a complete revolution. So when time is 32 minutes, the height is 15 meters. I'll plot a point at 32, 15. Now I can join the points with a smooth curve. I can also show the center line of the graph. To find the equation of the center line, I'll determine the mean of the y-coordinates of the maximum and minimum points. So, h equals 165 plus 15 divided by 2. H equals 90. I know the coordinates of the maximum point, so I'll use the cosine function to describe the motion. The equation of my function will have the form h at t equals a cosine b times t minus c plus d. The amplitude is 165 minus 90, which equals 75. So, I can replace a in the equation with 75. The period is 32, so b equals 2 pi divided by 32, which equals pi over 16. So, in my equation, I can replace b with pi over 16. If there was no phase shift, the y-intercept would be a maximum point. So, the phase shift is 16, and I can replace c in the equation with 16. The vertical translation is 90, so I can replace d with 90. So, an equation is h at t equals 75 cosine pi over 16 times t minus 16 plus 90. Part B. Assume a capsule is at the base of the wheel when it begins to rotate. Estimate the height of the capsule 20 minutes after the wheel begins to rotate. Give the answer to the nearest meter. I have the equation of my function, so I can substitute t equals 20. 20 minus 16 is 4. Pi over 16 times 4 is pi over 4. So, h at 20 equals approximately 143.0330. So, after 20 minutes, the height of the capsule is about 143 meters.
Okay, so for their example, there's the equation that they just came up with. But maybe you said, hey, I want to use a sine graph instead. And you could have done that. If we were using sine, the amplitude would have been exactly the same. Sine. The period would be exactly the same, so therefore the b value would be the same. And also the midline, the d value, would also be the same. The only thing that's going to change from a sine to a cosine is your phase shift. Let's look at where the phase shift would go in that one then. So then looking at the graph there, we can see if it was a sine graph, we're not looking for the maximum any longer. We're looking for where is the first going up through the midline. Sine goes up through the midline at the y-axis. We're looking where is the closest one of those. It's going to happen to be right here. And remember that this graph is cut up into 4 parts. Minimum to midline to maximum. So halfway in between the minimum and the maximum is where the midline would be, and that would be at 8. And because that was 8 to the right, we're going to go minus 8. And there's your sine graph for the exact same function. All right, a piston moves vertically in a cylinder starting from a minimum height. Every 20 seconds, the piston repeats its cycle from a minimum height of 15 centimeters to a maximum height of 35 and back to minimum of the 15. Okay, let's just do a quick little sketch. We know that it starts at a minimum, and they say that the minimum is 15 centimeters. And it goes to a maximum of 35. And it does this in 20 seconds. So it starts at the minimum, goes up to the maximum, back down to the minimum in 20 seconds. So if it goes one whole cycle in 20 seconds, that means it's going to be half in 10 seconds, which would mean it would be at the midline in half that distance at 5 seconds, and again at the midline in 15. So my recommendation for you always is to start with your A and your D, because they got nice formulas you can use. If you want to start with D, I'm going to actually start with D this time around, just so I can get where is that green line. The D is the midline. That's the average. So max plus the min divided by 2. So our max was 35, plus our min is 15, divided by 2. That'll give you 50 over 2, so that's 25. So I can put that in there at 25. Our amplitude is our A value. We could either do max minus the min divided by 2, or we could just say, what's the distance between the top and the midline? Oh, well, I know that that's going to be 10. I can see it there. So I've got those two values. The next one to do is your B value. The B is 2 pi divided by the period. Always got to use radians in this calculation here. Our period is how often or how long does it take to get back to the same point? And they told us every 20 seconds. So we've got then 2 pi over 20, which is going to be pi over 10. And it's not until this last point, the C value, that I have to decide, am I using a cosine or am I going to use a sine graph? If you're using the cosine graph, cosine, you're going to be looking for the maximum. And you'd be talking about that distance there. I'm going to change the color of it. If we're going to be using the sine, then we're going to be talking about this point here as our phase shift. So either way, you get the answer. Either talk about the maximum for cosine or talk about the midline going on the way up for sine. And I'm just going to use the cosine for this one. So in that case, my C value is that distance, which is 10. 10 to the right. Throw it into the equation. Y equals A cos of B bracket T minus C plus D. Boom. Let's throw down the sine one just because we can. Or y equals 10 sine pi over 10 t plus 25. All those are the same. The only thing that changes is that we're going t minus 5. All right, so we're going to graph this one. I'm just going to use the cosine one. If you graph either one, you're going to get the exact same graph. So you can check that out, try them, see that you will get the same graph. Make sure you look at your brackets. Bracket it correctly. And then we're going to graph it with a window that is going to be, well, the window that we used here. For the x, we went from 0 to 20 there. And scale doesn't matter. Go up by 1s, go up by 5s, doesn't matter. Y value, we're going from 0 up to 35, but I'm going to go a little bit further. I'm going to go to 40, just to make sure that I can see everything. Scale 1 really doesn't matter about the scale. Let's graph that. Good. Looks good. Perfect. That's looking good. And now we want to know for this one, what happens to the height 26 minutes after moving? Is that an x value or is that a y value? Well, the y values are in centimeters, the x value is in time. So we're going to do a value. So second value, and just plug in 26. Enter. Whoops. We can't find 26 seconds because I only said to go to 20 seconds. So the calculator's got to be able to see it. So we need to go further. Let's go past it. Let's go, hey, to, doesn't really matter. Let's double that. Let's go 40. And let's graph that. And then we'll be able to try it again. So I'm going to do 2 cycles. Up and down, up and down. Nice. It's like a jump rope. Let's do that again. Value. Let's find the 26 this time. And enter. Ah, there we can find it. 28.09, so about 28 centimeters. So 26 seconds. What did I say that number was? Was 28 centimeters. Okay, quickly looking back at what was in 6.5 there, we saw a graph that was dealing with daylight. Again, that's a sinusoidal function. The thing that you need to remember from these is if it's something about daylight, it repeats every year, 365 days. They're not going to tell you that that's the period. You need to realize, oh yeah, that's 1 year. And then each day of the year, starting in whichever day that they're giving is day 0. In this case, it's saying March 21st being day 0. Then you give each day after that, day 1, day 2, day 3. And in this case, to find the equation of that, we're going to use sine. The reason that we use sine is that it goes up through the midline. So, hey, we don't have to worry about a C value, a phase shift. C would be 0. So choose a sine for that. Although it could have been done with cosine if you looked at how far that's been shifted over the maximum. Again, go through, do your D and your A first. Then your B value, 2 pi divided by the period, which was 365. C value we discussed was 0 already. And plug her into your formula. Just for time, I'm going to actually bring the graph onto here so you can see the graph and we can work from there. But you would just plot the points, every point that we're given here. Okay, so after we've got these points plotted, now we have to start saying, okay, what does it kind of look like? And it kind of looks like it's going like that. So we look, hey, say, oh, this looks like we've got a nice graph going on. Sinusoidal. Now we have to decide, are we going to go with a cosine or with the sine? And I look at it and say, I can pick off the maximum point easier, so I'm going to use a cosine graph this time. So y equals a cos of b bracket, that would be this time, yeah, t minus c plus d. Let's start by finding a. So a is the max value minus the min value divided by 2. Well, my first maximum value I can see is here, and my first minimum value is there. So we go to the graph and see where are, or to the points and see what values did I plot there. So the first one is 2 and 6.5, and the first minimum there is at 8 and 1.4. So let's use the y coordinates of those. So So we've got 6.5 minus 1.4 divided by 2. And that equals 2.55. Let's do our d value next. Our d value is our max plus our min divided by 2. It's the average. Do the same thing. 6.5 plus 1.4 divided by 2. Plugging that into the calculator, we come up with 3.95. Next on the list, we're going to do our b value. It's always 2 pi divided by the period. Well, the period in these situations is going to be from a max to a max or a min to a min. So let's go from this max value to that max value, find out how far that is apart. And each one of these tick marks is worth 2 hours, so it's 2, 4, 6, 8, 10, 12 hours. So about 12 hours. 2 pi over 12, that gives me pi over 6. And the last thing is my c value, which is just how far did I move the max. Because I use cosine, the maximum should have been at the axes, but the maximum is moved over by 2 hours. So the c value is 2. And let's throw her down into the equation. Y equals a cos of b t minus c plus d. Could have done a sine as well if we really wanted to. Cos would have been easier here because we have the max value. So we punch it into the calculator with a window from the same window that we see there, 0 to 24 and 0 to 10. And then we graph it. Good, looks like that. At this point, now we want to find out what's going to happen. So we're looking for 1700 hours. That is 17 hours after midnight. That's an x value. So again, we're going to go value and plug in the value of 17, enter, and 3.95. So approximately 4 meters. Now, I know this wasn't part of this question, but what if it would have said, when is the first time that the tide will be at, let's say, 3 meters? Well, the way that you do it is go to y2 and make it equal to 3, and we graph and we find the intersection point. Where is the first intersection point where the graph is equal to 3? And then you just go second, find your intersection point, enter. Yeah, that's graph 1, that's graph 2. Oh, I need to be closer though. That's going to give me the second one right there. So I got to do that again and be closer to the first intersection point with my cursor. So slide it over, going. There we go. Enter, enter, and now it'll find the first intersection point, and that would have been at 5.7 hours. Okay, for yourself again, answer those 2 questions up, and then we will get her working in class. Even if you think it's hard, keep pushing on here. Life lessons with trigonometry and math.